Alright, well, welcome to our lecture recording for section 6.1. And in this recording, we're going to be introduced to the concept of power series, which is really the last major idea of calculus that uh, hasn't had really any treatment up until now. We're going to be making use of the things we learned in chapter 5, um, and we're going to be building a concept that really allows calculus to be applied to really pretty much everything else we want to apply it to the sciences, to engineering, to business applications. This is a very important bridge for us. I will mention today is April 2nd. It is finally beginning to feel like spring outside. It's nice and sunny. I can hear some birds singing. I can see a tree outside my window that's starting to bud. Still lots of bad things happening in the world. A lot of people are sick and in a lot of trouble. But there are some things to be cheerful about. Oh, something to think about as we get into our lecture. Alright. So here's our outline for section 6.1. We'll start with a discussion of why we're interested in power series. So here's some functions that I know you're familiar with. We've used them previously in this course, and you've used them in courses prior to this one. Functions like sine of x and y equals e to the x and y equals natural log of x. We think of these as transcending algebra because you can't really write formulas for them without using the concepts of calculus. Limits, derivatives, integrals. In fact, prior to calculus, we don't really even try to write formulas for them. They're just buttons on our calculators. Okay. And it's because we need calculus to create those formulas. Now, because we think of these functions as transcending algebra, we refer to them as transcendental functions. So, for example, here's one that we've gone over in this class. To write a formula for the natural log function, we actually need to use an integral, which is one of the calculus operations. Okay, the natural log of x is defined to be the integral from 1 to x of 1 over t integrated with respect to t. Okay, so that's a transcendental function. It transcends algebra because I can't write a formula for it just using algebra. I need calculus. As a counterexample, here's a finite polynomial function, y equals x squared plus 2. Now, all we really need to write a formula for this function is just basic algebraic operations, powers, addition. Other algebraic operations are subtraction, multiplication, division, roots. Okay, if I can build the function just using those things and without having to use limits, derivatives, or integrals, then I would call it an algebraic function. Now here's the thing that we have to balance. Pretty much all naturally occurring functions are transcendental. And when I say naturally occurring, I mean both things that describe natural relationships, like if I built a function that gave me the population of a group of sparrows over time, yeah, that would probably be a transcendental function. It's probably something like e to the x, okay, or something that would involve e to the x in some way, okay. But even functions that arise in the course of very artificial things, like designing electrical circuits, for example. Maybe I would create a function that was giving me the relationship between the charge on a capacitor as a function of time. Okay, that also would be a transcendental function. Okay, most functions, unless we design them to be algebraic, are going to be transcendental. Okay. However, the flip side is that algebraic functions, especially polynomials, are a lot easier to work with. I mean, for starters, it's easier to plug things into them because they have very straightforward formulas, and we know how to do the algebraic operations. But it's also easier to do calculus with algebraic functions. So, when you consider that dichotomy of what types of functions actually emerge in application and what types of functions are easy to work with mathematically, it's kind of natural to wonder if there's a way to kind of bridge that gap. And in fact, there is a way to bridge that gap, and people have been using it for hundreds of years. Okay, it's the concept of power series, which is what this section is all about. Alright, we're going to start by building a power series for y equals e to the x, because this is, of those examples of transcendental functions we gave, this is perhaps the most straightforward. Okay, the most important characteristic of this function from the standpoint of application is the fact that y equals e to the x is equal to its own derivative. Okay, we showed that to be true earlier in the course. Okay, but that makes it very useful in differential equations, equations that compare a function to its own derivative. A lot of you will eventually take a course on differential equations, and what you're going to find is that as we learn how to solve different types of differential equations in that class, we keep coming back and making use of the fact that this function is equal to its own derivative. Okay, we can use that over and over again to solve more and more complex differential equations. The differential equations are one of the most useful tools for describing especially quantities that are changing over time. Okay, if we want to create a mathematical model for something that's dynamic, changing over time, that's almost always going to take the form of a differential equation. Okay. Alright, so first of all, here's a good point to make. Let's discuss how we would know that no finite polynomial could have this property. Okay, this is probably worth looking at an example or two of. Alright, so here's an example of a finite polynomial. By finite, I mean it has a finite number of terms. Okay, just 4 terms. If I take the derivative, we know how this works. Okay, polynomials are easy to differentiate. I bring that power down, and I get 6x squared minus 18x plus 3. Now notice that because of this action of bringing the power down and then reducing the power by 1, the derivative always has a degree 1 lower than the original function. Okay, and that's going to be true whether we start with x to the 3 or x to the 13 or x to any power. Okay, the first thing we're going to do is drop the degree of the highest degree term by 1, which means that pretty much no matter what we start with, we're going to wind up with a derivative that has a lower degree than the original function, which means that there's pretty much no way for a function that is a finite polynomial to ever be equal to its own derivative. Okay. However, as people started thinking about problems like this, they really didn't want to let go of the idea that we might be able to use a polynomial as a proxy for y equals e to the x, because polynomials are so easy to work with in every way. It dawned on people pretty early on, I mean hundreds of years ago, even before we really got serious about modern calculus. Okay, it occurred to people that one way we could get around this problem was by having an infinite number of terms in the polynomial. So let me show you what we have in mind here. Okay, this would be moving into part B of our example. So let's say that maybe there's an infinite polynomial, a polynomial with infinitely many terms, that's equal to y equals e to the x. Okay, now we don't know that there is, okay, but let's assume that maybe there is. Okay, notice that if I were to take the derivative of such a polynomial, okay, of course the derivative of e to the x is itself, but if I take the derivative of the polynomial, okay, the constant term, whatever that is, that would have to go away. Okay, the x term would become a constant term, So that c1 would now be a constant by itself. The x squared term, whatever its constant is, would be multiplied by 2. So it would be 2 times c2x. And then the x cubed term would become an x squared term. And the x to the fourth term would become an x cubed term. The x to the fifth term would become an x to the fourth term. But no matter how far we go, because there's infinitely many terms here, okay, and we have degrees going from 0 up to infinity, there's always another term to differentiate, so there's still no upper bound to how high my degrees go. Okay, so I haven't really lost anything from the degree here. Okay, you could think of the degree, I guess, as being infinity. It's still infinity. Okay, which means it's entirely possible that these two polynomials could be equal. Okay, with finite polynomials, there was just no hope of it because we were always going to drop a degree. But with an infinite number of terms, we don't lose a degree when we differentiate. Now, before I go any further, let me make a little observation here. Okay, since y is e to the x, we know that y of 0 would be e to the 0, which would be 1. But if there's a polynomial, an infinite polynomial, that's equal to e to the x, then when I plug 0 into that, all the terms would disappear except for the constant term. Okay, so what I called c sub 0, the first constant, the constant term, would have to be a 1. Okay, c sub 0 would have to be 1, but check this out. C sub 0 would have to be 1, but because we want y to equal y prime, these two polynomials, the original one and the derivative, would have to match up term by term. Two polynomials can only be equal if they have the same constant terms and the same coefficients of x and the same coefficients of x squared and so on. So because we want this property, okay, we consider this to be the most important property of this function. Okay, we can say, hey, if c0 is 1, c1 has to be 1. So c1 must also be 1. But now there's kind of a domino effect, because if I make the next comparison, I can say, and then 2c2, it's got to equal c1, so it's got to be 1, which implies that c2 is 1/2. And let's make the next comparison. If I compare the coefficients of the x squared terms, 3c3 has got to equal c2. But c2 was 1/2. So c3 would be, well, I divide by 3, I guess I'd get 1/6, but let me write it like this. Okay, I'm going to write it as 2 times 3. And let's make another comparison. If I compare the coefficients of the degree 3 terms, I can see that 4c4 would have to equal c3. So 4c4 would equal, this is c3, 1 over 2 times 3. So if I divide both sides by 4, I can say c4 is 1 over 2 times 3 times 4. And I think you can see where this pattern is going to go. You know, I think we can go ahead and say c5 is probably going to wind up being 1 over 2 times 3 times 4 times 5. in C6, well, that's going to be 1 over 2 times 3 times 4 times 5 times 6, and it's just going to keep going like that. And you might have already realized that what we're building is factorials. Okay, 6 factorial is 6 times 5 times 4 times 3 times 2, and then technically also times 1, but multiplying by 1 wouldn't change anything. So we can go ahead and say that denominator is 6 factorial. Okay, so C6 is really 1 over 6 factorial. C5 is 1 over 5 factorial. C4 is 1 over 4 factorial. C3 is 1 over 3 factorial. C2 is 1 over 2 factorial. 2 factorial is 2. I don't know why I keep writing a C there. Yeah, 1 over 2 factorial. And really, since 1 factorial is 1, I guess we could go ahead and say, well, C1 was 1 over 1 factorial. Okay. Now, there's something I haven't mentioned previously, but here's a point of definition. We define, we define 0 factorial to be 1. Okay, and the reason we do that is actually because of what we're doing right here. It's so that we can say C1 equals 1, which is 1 over 1 factorial, and C sub 0 also 1, and we can say that's 1 over 0 factorial. Okay. What we're trying to do is we're trying to make it so that we can write all of these coefficients in the same form. Okay, and then we can just go back and fill the coefficients in. 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. Okay, and we can say in general, if there is an infinite polynomial that equals y equals e to the x. So technically we haven't proven that there is, we've just proven that if there is one, its coefficients would have to look like this. So if there is an infinite polynomial that equals y equals e to the x, then it is the sum from n equals 0 to infinity of 1 over n factorial times x to the n. Okay, so when n is 0, we'd have 1 over 0 factorial, which is 1, and x to the 0 would be 1. And then when n is 1, we would get just an x. When n is 2, we'd get 1 over 2 factorial x squared, and 1 over 3 factorial x cubed, and then so on like that. Okay. Again, we haven't really proven that this polynomial does in fact equal y equals e to the x. We've just shown that if there is an infinite polynomial that equals it, it would have to be that. Now, here's a way we could do a little test. We could do an approximation. Okay, we could do an approximation. So let's say it like this. Let's say if so this is moving on to, let me flip back to the outline real quick, just so we remember where we are. We did part B. Now part C. We're going to move into part C here. Use the first 7 terms of the polynomial to approximate the value of e. Okay. Alright, so if y equals e to the x equals the sum from n equals 0 to infinity of 1 over n factorial x to the n, then we can approximate it with a partial sum. So we could say e to the x is approximately equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4. I said 7 terms, so we'll have to go up to degree 6 since we start with degree 0. 1 over 5 factorial x to the 5 plus 1 over 6 factorial x to the 6. So I'm going to cut it off at 6 terms. This would be a partial sum of this infinite sum. But if this infinite sum equals e to the x, then this partial sum should be an approximation. And furthermore, I'm going to go out on a limb and say it should be a pretty good approximation because factorials grow fast. And since they're in the denominator, the terms are shrinking fast. So if this thing really is converging on e to the x, then it should be the case that we should be pretty close after even just a handful of terms. Okay, so if e to the x can be approximated with this finite polynomial, then e, which would be e to the 1, would be approximately equal to what I would get if I plugged 1 in for x into this polynomial. So 1 plus 1 plus a half plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial. Alright, let's put that in the calculator and see if we get a number that looks something like e. Alright, so 1 plus 1. Let's see if I can make the focus any better. Yeah, maybe that's better. Plus 1 divided by 2, plus 1 divided by 3. So remember, I got to press my probability key and then select my factorial symbol. And plus 1 divided by 4 factorial plus 1 divided by 5 factorial, and one more, 1 divided by 6 factorial. Alright, so with any luck this will be fairly close to e, which is 2.1828 I'm sorry, 2.71828, and then it goes on. Well, that actually looks like it's correct out to maybe 3 decimal places. That's a pretty decent approximation. So let me write that down here. The approximation given by our polynomial is 2.718, and what's it say there? 0, and then it looks like a bunch of 5s. 5, 5, 5, 5, 6. Now, my calculator can give me a better approximation for e, 2.718281828. Now, why do I say better approximation? Well, because my calculator just gave me, let me see, I have 9 decimal places, so it gave me basically a 9 decimal place approximation. Okay, this was a 3 decimal place approximation, but presumably if I had tacked on more terms I could have gotten more decimals accurate. In fact, let's just see real quick. I think I left off with 6 factorial, so maybe if I tack on plus 1 divided by 7 factorial, let's see what that does. Well, let me see, that gives me, looks like that gives me 1 more decimal place of accuracy. What if I do, let's do another one. Plus 1 divided by 8 factorial. Well, you know what? That number, 2.7182, if you rounded it to 5 decimal places, it would be 28. Okay, so now we have 5 decimal places of accuracy. So yeah, this is converging quickly. I mean, it's conceivable that the way the calculator got this number was by just using enough terms of this series. Okay, this is what power series can do for us. I mean, this is a really important question in mathematics that we've completely glossed over up to now. We've been introducing these transcendental functions in calculus and even before calculus because they were such powerful things that could solve all these interesting problems. But we were really kind of glossing over things like, how do I get sine of, I don't know, 1.2? Okay, well, this is one way you can do that. It's through power series. In fact, this was the original way of answering questions like that, which has pretty big implications for scientific applications like astronomy. In fact, that's what sine and cosine were invented for, was for studying astronomy in ancient Greece. But since the ancient Greeks didn't know how to get really accurate values past 1 or 2 decimal places, there was really a limit to how good their astronomical calculations could ever be. And that's why they didn't have very good models. Sometimes we pick on the ancient Greeks for thinking that everything revolved around the Earth, but based on the data they had, their models were actually pretty reasonable. The problem is, they had really crappy data. And they had crappy data because they didn't know how to do this. Now, we're going to start learning how people figured out how to do this sort of thing to get really accurate values of transcendental functions. All right, let me go back to the outline. All right, so we did part C. Now let's do part D. Let's do kind of a visual of what we had going on there. All right, so here I am in Desmos, and I'm going to start by entering in y equals e to the x. Okay, I think we're pretty familiar with what this thing looks like. Okay, we know this function goes to infinity and grows pretty quickly as x goes to the right, but going to the left, it asymptotically approaches y equals 0. Okay, it's a function we've looked at many times in this course and you've seen in other courses. Now, let's start approximating it using our infinite polynomial, but we're going to use finite polynomials where we add on more and more terms from our infinite polynomial. So let's do y equals 1 plus x, the first 2 terms of our infinite polynomial. All this is this is the line that's tangent to y equals e to the x at x equals 0. Remember, we used the fact that we knew the y value of y equals e to the x at x equals 0. That's the one and only x value where it's really easy to come up with a y value and know all the decimal places for this function. It's kind of a key. To build a power series for a function, you need to have at least one x value where you know the y value of the function. Okay. So this first degree polynomial approximation, where we just take the first 2 terms of our infinite polynomial, is really just giving us a tangent line, something that matches the curve out to the first derivative. Okay, it matches both the y value of the function and it matches the first derivative of the function. Okay, as the first derivative of y equals x plus 1 is 1, so it's just a line with a slope of 1 going through the point 0, 1. When I add the second term of this series, y equals x squared divided by 2, and I can even put factorial, that won't change anything. Okay, notice that my, actually, I'm going to put that down here and put up here y equals x plus 1. So notice, of course, this is a second degree polynomial, so this new approximation is a parabola. Okay, now here's the thing I want you to see. Notice how that parabola, if we start moving out from 0, 1, that parabola stays closer to y equals e to the x longer than the line does. Okay, if we really home in on the point 0, 1, both the parabola and the line kind of merge with y equals e to the x if we zoom in far enough. Okay, let me zoom in maybe just a touch more. I mean, yeah, I zoom in far enough and all three look the same to me. The line, the parabola, the transcendental curve, they look like the same line. But when I start zooming out, I can see the line breaking off the transcendental curve sooner than the parabola does. The line is a decent approximator of the transcendental curve, but only right around x equals 0. Okay, the parabola is a decent approximator for a bigger interval. Now eventually it pulls off of the transcendental curve too, but it stays closer longer. Now, let's see what happens if I throw on another term. Let's do plus x cubed divided by 3 factorial. Alright, so that gives me this green curve. So notice the green curve, let me see, it's going up to the right but down to the left. Yeah, it's cubic. The thing I want you to see about that green curve is that it stays close to the original black transcendental curve even longer than the parabola does. Okay, basically the more terms we add on, the more flexible we make the polynomial. The more flexible we make it, the longer it can stay close to the transcendental curve before it peels off. Okay, the tangent line was basically just something that matched the original function at the first derivative and the function itself. The second degree approximation would match the original function at the first and second derivatives. This one matches it first, second, and third derivatives. Okay, and if I add in more, I can make it stay close even longer. In fact, let's start automating this a little bit. Let's do y equals a sum where n goes from 1, let's say up to, well, let's let the upper limit be variable. We'll call it big N. Okay, and I want my nth term to be 1 over n factorial times x to the n. Okay. Oops, you know what? I made a little mistake. This sum should actually start with a 0. That's why my tangent line was not matching up there. Alright. Now, it recognized when I put a variable rather than a number at the top of this sum, it realized that I might want to be changing that variable, so it let me add a slider. Let me customize my slider a little bit. We'll say the slider can go from 0 up to 10 in steps of 1, because it's got to be whole numbers. And then, you know what, let's turn on an animation here, maybe even slow that down. Alright, so there's n equals 1. Give it a second. So it's just basically the 1 plus x. There's when n is 2, and then 3, and then 4. Now watch it. Watch in here between -2 and 3. Notice that every time it adds another degree, the approximating curve stays closer to the true curve longer. Okay? In fact, in theory, if I increase the limit here, let's say let's let n go up to 20, and then maybe step our picture out a little bit. So every time it increases, watch how we can get further and further over. It's getting further and further over on this side too, we just can't see it because it's already off the screen. Okay. So here's the idea I wanted you guys to get out of that. I think I'll pause that little animation. What I wanted you to get is that the more terms we add, the further out we can go from where we centered the series and still have a finite number of terms that approximate the transcendental function very well. I will tell you that what we do a lot of times in science and engineering applications is we just use one or two terms of a power series, and that gives us an approximation that's only good in a little interval, but sometimes that little interval is all we want. Okay? And if we want to go beyond that interval, sometimes we have to go back and add more terms. That's why mathematical models sometimes have to be changed when the domain of the model changes. And I'll give you a good example. We typically use a linear model to give the relationship between speed and drag when an object is moving through the air. However, if the object's going really fast, we bump it up to a degree 2 model. And the reason is, speed is like the x. If I let x get too far from 0, with a linear model, the model starts to not be very accurate. But if I bump it up a degree and let it be degree 2 instead of degree 1, then I can get a bigger interval of accuracy, and so I can have a model that's good for a bigger range of, in this case, speeds. So that's just one example. If I wanted a perfect mathematical model for the relationship between speed and drag for an object moving through the air, I would have to have an infinite power series, because it's not an algebraic relationship, it's a natural relationship. Natural relationships are almost always transcendental, and this one is. So if I wanted one that would be good for all speeds, I would have to use infinitely many terms. But I don't usually need a model that's good for all possible speeds. There's usually a range of speeds that I'm interested in, and therefore I can restrict the model to a lower degree to make other things simpler. That's very, very common in the formulas you see in physics. They involve the first 2 or 3 terms of a power series to get a mathematical model that's good enough for what we're studying. Alright, let's go back to our outline. Okay, we completed our first example. Okay, now that we've been through that, I think we can look at the definition of power series in our book, and we'll get some idea of what this concept is about now that we've actually kind of built one for y equals e to the x. Alright, so here's page 532 of our book. This is section 6.1. Okay, key definition for this section, the definition of a power series. Okay, so a series that has the form of an infinite polynomial, constant term, degree 1 term, degree 2 term, and then so on. So basically, just a bunch of coefficients times x to a power that's increasing is what we would call a power series. And in this case, this is like the one we just built. We would say it's a power series that's centered at x equals 0. Okay? The point we center a series at is, remember how I said we need to know at least one x value where we know the y value of the function that we're building a power series for? That's the value that we're centering our series around. Okay? Very often we center them at 0 because 0 is very often the easiest x value to get a y value for. But we don't always. Sometimes we have to center a power series around a different number. Sometimes it doesn't matter. Sometimes it does. Okay? If I have to center it around some other number, we'll say generically x equals a, then instead of having x to the n in the nth term, I would have x minus a to the n in the nth term. Here is a little something that's worth mentioning. It's really just kind of a little detail, but it needs to be mentioned because otherwise our definition lacks a little bit in precision. We're assuming that x to the 0 equals 1, which is true for every x value except x equals 0. But for purposes of this definition, we're going to assume that x to the 0 equals 1 even when x is 0. Okay? that basically makes it so that this formula for the nth term generates all of these terms over on the right side. Okay, otherwise we'd have to have one term outside the series, and that would just be a little less clean. So, we kind of throw in this little proviso up front. All right, tiny bit of history, just because this is such a big idea. As far as we know, the first people to ever use power series were Indian astronomers in the 1300s. They figured out how to use, they constructed power series for sine and cosine, okay, and that allowed them to do much more accurate astronomical calculations than what the Greeks had ever done. The ideas of sine and cosine had come to India in ancient times when Alexander the Great conquered part of India, and he brought elements of Greek culture into India, including some of the Greek ideas about astronomy, like using sine and cosine to measure arcs in the sky. But eventually the Indians figured out how to really improve on these concepts. The Greeks didn't really know how to calculate sine and cosine past 1 or 2 decimal places. But the Indians figured out eventually, many hundreds of years later, the 1300s, how to build power series. If you've got power series for sine and cosine, then you can create as many decimal places of accuracy as you need. And sometimes you need a lot in astronomical calculations, because you're multiplying sine and cosine sometimes by millions of miles, and a tiny little error in your sine value, if your sine is, say, only good to 3 decimal places and you multiply it by 10 million, well, now an error that was only a thousandth is now thousands. Okay, it makes a big difference. But if you could get sine worked out to 7 or 8 decimal places, now you can keep your error small even when you multiply by big numbers. That was huge. And I honestly can't tell you how huge this was. This spread quickly. Okay, not necessarily the method by how they constructed this. We really don't know how the Indians constructed power series. It's kind of assumed that because they had them, they must have developed some of what we now call calculus. Otherwise, they had some way of building power series that was completely different from what I've been showing you here. But if they did, that's been lost to time. We don't know how they did it. But the results of their calculations were translated into tables of sine and cosine values that got published all over the world in the next century, especially after 1450, when the Gutenberg printing press was invented. These ideas started spreading really fast. They were brought into Europe right around the time of the Gutenberg printing press by scholars fleeing Byzantium, because they'd been run out by conquerors. And then the printing press really helped all kinds of ideas spread very quickly, but in particular, tables of sine and cosine values that had been developed in India and the Middle East started circulating through Europe very quickly. Some of the implications of that, one was that now all of a sudden open water navigation was not so scary at all. If you can compute accurate sine and cosine values, you can navigate without being able to see anything except stars, which is part of why in very short order people were crossing oceans. Columbus was crossing the Atlantic, going to some islands in the Caribbean, going back to Europe, going back to the islands, more or less going exactly where he wanted to go. Da Gama was going across the Indian Ocean, coming back, going. Navigation improved very quickly. But so did a lot of ideas in science. It was only a few decades after that that Copernicus came out with his heliocentric model, where he said, hey, stuff doesn't revolve around the Earth. Earth revolves around the sun, and so does all this other stuff we've been looking at. And the reason was, once he actually had accurate values of sine and cosine, he could see that the mathematical models that had seemed so reasonable to the Greeks didn't seem reasonable anymore. This was very transformative stuff. Okay, transformed world trade, transformed science. These is big idea stuff here. What we think of as calculus, where derivatives and integrals and limits were all kind of integrated together in a unified discipline. We usually think of that as emerging in Europe in the late 1600s, although it was really kind of a consolidation of ideas that had been building for many centuries. When modern calculus really started to come together in the time of Isaac Newton and Gottfried Leibniz, all of the major early figures like Newton and Leibniz and the Bernoullis realized very quickly that power series were very much at the heart of this discipline. So like I said, this is kind of like the last big idea that we hadn't introduced in the first 2 semesters of calculus, and this is what chapter 6 is going to be about. Now, I'm going to use what we've learned previously about geometric series to build some more power series. In particular, I'm going to use them to build power series for the function y equals 1 over 1 minus x. Now this function is not transcendental. It's an algebraic function. I mean, all the operations here, division, subtraction, that's all algebraic. Okay, so we wouldn't necessarily need a power series for this function, but it's very easy to build one for it because we can use formulas we developed for geometric series, and doing so will give us some insights into how power series behave. So we're going to use the formula that says if our common ratio r has an absolute value less than 1, then a geometric series of the form, oh, you know what, there's actually a little error here, that should say 0. A geometric series of the form sum from n equals 0 to infinity of a times r to the n minus 1, that infinite series will add up to a divided by 1 minus r if r has an absolute value less than 1. So we can actually kind of use that in reverse to take the fraction 1 over 1 minus x and transform that into an infinite series. So here's our function, y equals 1 over 1 minus x, and then here's our formula. Our formula is that a over 1 minus r should equal a sum from n equals 0 to infinity of a times r to the n minus 1. So in other words, that would be a plus ar plus ar squared plus ar cubed, and then so on. Oh, I left out my r there. Let's flip that in there. So just following our pattern there, we can say that this should be the sum from n equals 0 to infinity of, alright, so matching stuff up, a would be 1, and then r would be x. So that would be 1 times x to the n minus 1, okay, if the absolute value of x is less than 1. Okay, so let me see. If n is 0, this would be x to the 0, so the first term would be 1, and then x squared, and then x cubed, and then x to the 4th, and so on. So again, let's go back to Desmos and get kind of a visual of what's happening here. Alright, so we get rid of u, we don't need this slider. We can say y equals 1 over 1 minus x. Alright, so here's our function. Okay, notice this function has a vertical asymptote at x equals 1. Okay, if we thought about it, I think we would have known in advance, because clearly 1 makes the denominator 0 but doesn't make the numerator 0. And in fact, you know what, just for visualization, I'm going to put x equals 1 in the picture, just to kind of remind us that this function has a vertical asymptote at x equals 1. Alright, now let's start putting in terms of our of our power series. Starting with the first one, y equals 1. Okay, y equals 1 really only matches up with the original function right at x equals 0. It matches up there because x equals 0 is where our power series is centered. Okay, now let's do y equals 1 plus x. Alright, now we're up to degree 1, so we have the tangent line of the original function at x equals 0. I think I'm going to zoom in a bit. Alright, let's do y equals 1 plus x squared. Alright, so now again, I can see that that gives me a parabola, and my parabola hugs my original curve. So remember, the original curve is red. You can kind of go by this color code on the side. The parabola hugs close to that curve further out from 0 than the tangent line does. Okay, I can see it even more clearly on the right hand side here. Okay, and presumably if I were to tack on another term, in fact, let's just do that right in here, plus x to the 3. Okay, that would give me something that would hug even longer. So you know what, again, let's use some summation and do y equals a sum from n equals 0 to capital N of x to the little n, and we'll add a slider, and again let's just say we're going to let big N go from 0 up to 10, so we can get up to a 10th degree term, and we'll do that in steps of 1. Alright, so now as I advance my slider, alright, there's my polynomial again when I let the degree be 2. There's my third degree polynomial instead of my parabola. Okay, there's my fourth degree. There's my fifth degree. So again, you can see that the higher the degree, the further over from 0 my polynomial stays close to the curve. Alright, so let's jump up, 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 up. You know what? It actually kind of starts to look like we're not gaining a lot of ground. It's just kind of flipping up and down, but it seems like we're not going to stay close past -1. I didn't have that same restriction with y equals e to the x. It seemed like there I just kept moving to the left, hugging it closer longer and longer. Let's see what happens if we bump this up. Maybe let's let n go as high as 100. Alright, so now bump, 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 and big, 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 big. Well, now I'm almost all the way to the -1, but then past that, it's nowhere near the curve. And it doesn't actually seem to matter how big I make the degree. Okay, it's almost like there's a glass wall there and I can't approximate past -1. Okay, here's the problem. The problem is the function, the original function, has a discontinuity over here at x equals 1. Okay, that discontinuity kind of screws up my polynomial approximation because polynomials don't have discontinuities in them. So there's really no way my polynomial could hop across this vertical asymptote and start approximating the rest of the function y equals 1 over 1 minus x. That vertical asymptote is effectively a glass wall that I can't get through. But it turns out to be the case that if we're limited on our interval of convergence, if there's only a limited interval where the power series is going to converge on the function it's approximating, then if it's limited, those intervals are always symmetric. They're symmetric about whatever point we centered it on. Since this one was centered at 0, and I can only go a distance of 1 to the right of 0, I'm actually limited in the other direction. Now look, this is no big surprise in this case, okay, because we already said that this would only be good for x values whose absolute value is less than 1. Okay, If I say that the absolute value of x is less than 1, I'm literally saying its distance from 0 is less than 1. So if I say absolute value of x is less than 1, I'm saying x is less than 1, but also that it's greater than negative 1. So from the get-go, because this power series is really a geometric series, I only expected it to be a valid approximation for x between negative 1 and 1. Outside of that, this geometric series is divergent, which means it really has no hope of converging on a finite function. So no big surprise there, but this actually turns out to be a characteristic of power series. Sometimes they converge for all x values, which means if I make the degree big enough, I can get it to be a good approximation for the original function, no matter how far out I want to go. But sometimes there's a limited interval of convergence. Alright, let's go back to the outline. So we did part A, we did part B. Now, here's a way to get around that limitation. Let's say that I needed a power series that approximated this function for values bigger than 1, so I need to get on the other side of that vertical asymptote. Okay, what that means is I'm going to have to use the second part of my definition. I'm going to have to use the fact that power series can be centered at x values other than 0. Okay, now let's look back at the definition real quick. If I want my power series to be centered at x equals a, okay, or a is some number, then the terms of my power series need to look like x minus a. Okay, but if I remember that I'm using geometric series to create my power series, that means that I need x minus 3 here instead of x. Well, where did this x come from? It was the r value. And r is just whatever is subtracted from 1 in the denominator of this fraction. So I'm going to actually have to do a little bit of algebraic manipulation to make it so that instead of having something over 1 minus x, I have something over 1 minus the quantity x minus 3. Okay, if I can manipulate this fraction to look like that, then x minus 3 is my r, x minus 3 goes over here and gets raised to powers of n, and I have a power series that's centered at 3 instead of 0. But how do we do that? It's actually easier than you might think. Okay, this actually turns out to be one of those things that once you know what you want, you just make it happen. You might be thinking, what does that mean? But of course I'm going to show you. Here's what I mean by you just make it happen. Okay, since I have figured out that I want to have x minus 3 here in the r position, I'm going to put it there. But of course I want to do it without really changing the function. So I need to do something that offsets the change I made. So I'm going to replace x with x minus 3 plus 3, which is equivalent to x. Okay. And that allows me to get my x minus 3. However, I got to now do something with that plus 3. Okay, so this is 1 over 1 minus, I'm going to distribute the minus to the quantity x minus 3, but also to that plus 3. So that'll give me a minus 3 at the back. Now, in order for me to turn this into a geometric series, I have to be able to use the formula a over 1 minus r equals a plus ar plus ar squared plus ar cubed and so on. Okay, now a can be anything. R I'm trying to get to be something specific. Okay, the formula doesn't really permit me to have another term down here, so I need to combine that with my 1. So 1 minus 3 is minus 2 minus x minus 3. But that actually creates another problem for me, because the formula requires me to have a 1 right there. Okay? But I can get a 1 there. I just need to multiply the top and bottom both by negative 1/2. Because if I do that, when the negative 1/2 distributes through the bottom, I get a 1 back there. Alright, so now I get negative 1/2 over 1 minus x minus 3. X minus 3 was multiplied by negative 1/2, so now it's over negative 2. Okay, now I could make this plus and plus, but I'm not doing that because I want to continue to match up with this form, a over 1 minus r. Okay, I needed to get that 1 matching. Now I can say, hey, this is a, and this whole thing here, the whole thing that's subtracted from 1, that's my r. Okay, so a equals negative 1/2, r equals x minus 3 over negative 2. So now I can say that my fraction y equals 1 over 1 minus x equals, so that's my a, and then this is my r, so negative 1/2 plus negative 1/2 times x minus 3 over negative 2 plus negative 1/2 times x minus 3 over negative 2 squared, and then the sum continues. Okay, so that would be a sum from n equals 0 to infinity of negative 1/2. Okay, negative 1/2 times x minus 3 over negative 2 to the n minus 1. Okay, but there's a caveat. Okay, this equivalence, that this fraction can become this infinite series, assumes that our r value has an absolute value that is less than negative 1. Okay, so there's a big if here. So if the absolute value of x minus 3 over negative 2 is less than 1, and that's only true, so that's true if and only if the quantity x minus 3 over negative 2 is between 1 and negative 1. Now, I got to do a little rearranging there. If I multiply everything through by negative 2, then that would give me 2 and x minus 3 and negative 2. But remember, when you multiply inequalities by negatives, you flip them. And then, well, let me see. I got to add 3 to everything. So I'm running out of space here, but I can just put that on another piece of paper. So then that would be true if and only if, add 3 to everything, 5 is greater than x is greater than 1. Alright, so remember, our power series was centered at 3, and it should be convergent out to these x values. So it should be the case that when I start putting this stuff into Desmos, I'm going to see curves that are approximating not near x equals 0, but near x equals 3, and they should be able to approximate the curve out to these endpoints. Let's see what that looks like. Okay, so I'm going to get rid of this, and this, and this. Okay, and I'm going to put in a sum from n equals 0 to big N. And remember, my a value is negative 1/2. And then my r value was x minus 3. but then I'm going to highlight that because I want to put all of that over -2, and then we've got to raise that to n minus 1. No, I say n minus 1. Alright, now we'll add in our slider. Okay, something's not quite right there, and I had to think about it for a second. The thing that I messed up is because we're letting n start at 0, the power doesn't need to be n minus 1. It can be n. Since n starting at 0, the first power will still be 0. Okay, so little correction there. In the past, I've always done geometric series with a power of n minus 1. But here, we're letting the power be n to match the form of power series, and letting n start at 0 rather than 1. Alright, so now it looks correct. So looking at my slider here, big N is 1, so we're getting a degree 1 polynomial approximation of our red curve that's centered at 3. So I've got a tangent line that is a good approximation for the red curve in the vicinity of 3. Now let's let our slider go from 0 up to 10 in steps of 1, so that we can start increasing the degree of our polynomial approximation. Alright, there's a parabola, follows it even further. Degree 3, further, 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 further. Okay. We're getting further, but notice that we're now not really spreading out very quickly. And even if I start using an obscene number of terms, like 100, let's back that up to like 10 and kind of slowly, you can see that I'm not really gaining ground here. Okay, if you watch real closely as the curve flips up and down, you can see that our approximation is staying close to the red curve a little bit longer. You know, it's staying closer and closer to 5. Okay, but 5 seems to again be kind of a barrier for it. Okay, and we know why. It's because once x goes past 5, the r value of our geometric series is too big to converge. So this power series is only ever going to give me good approximations for y equals 1 over 1 minus x in the interval from 1 over to 5. Okay, past that, you know, over here on this curve, or past 5 over on the right side, it's not going to be any good for us. Okay, so now we've kind of seen the things that can happen. We've seen, you know, it could be that the power series could conceivably be used to approximate the entire function, or maybe it would only be good for a part of it. So let's go back to our outline. And we're going to look at a page in the book that talks about convergence of power series, page 533. Okay, so coming down one page, theorem 6.1, convergence of power series. Okay, it's telling us there's 3 things that could happen. If we've got a power series that's centered on the number a, then one thing that could happen is that the series only converges at a. Okay, now it kind of has to converge at a, because if nothing else, when you plug a in for x, it makes every term except 1 zero out. Okay, c sub 0 would still be there, but it basically blanks out all the other terms. So the power series is going to match the function add x equals a by design, but sometimes that's the only place where it could ever match it. Okay, that's the only place where it converges. Obviously, we're not really interested in power series like that because they're not good for anything, but that's a possibility. Second possibility is that they converge for all real numbers. Third possibility is that there is some number r such that the series converges if the absolute value of x minus a is less than r, and diverges if x minus a is greater than r. Okay. And then there's some ambiguity at the endpoints, which is something we would have to talk about one at a time. But what this means is, if it isn't the case that the power series converges for all x values, or just at the x value where it's centered, then there is some interval, finite interval of convergence, and that interval of convergence goes the same distance on both sides. Okay? Because here's the thing, let's home in on this. If the absolute value of x minus a is less than r, then that would translate like this. Absolute value of x minus a is less than r. That's true only if and only if x minus a is less than r but also greater than negative r. And then if I add a all the way through, I would get a minus r is less than x is less than a plus r. So remember, if a is the place where the power series is centered, then in this third case, my interval of convergence is everywhere from a minus r to a plus r. So that third possibility is there's a finite interval of convergence that's centered on a, and it goes out the same distance from either side of a. All right. Let's also look at the definitions of interval of convergence and radiance of convergence, which are really just giving terms to what we were talking about. And I had it in my head that they were up here. Alright, so this is actually the next page of the book. Okay, and the next page, on page 534, the book talks about the interval of convergence, which is just the set of all x values where it converges, and the radius of convergence, which is that r value from the definition. Okay, so the interval of convergence can either just be the point a, or it can be all real numbers, or it can be a finite interval centered on a, and the distance from a to the edge of that interval is what we call big R, the radius of convergence. Alright, let's do some examples. Starting with number 20 in the book. Okay, so scrolling down to our homework set. Let's see what the instructions are here. It says, so the instructions are back here on this page. In the following exercises, find the radius of convergence, big R, and the interval of convergence for the given power series. Okay. So, number 20 is actually a power series that we've already talked about. This is the power series for e to the x. Well, actually it's the power series for e to the x, but notice how it starts at n equals 1. So technically it's the power series for e to the x minus 1, because it's leaving off the 1 at the beginning. Okay, but it really shouldn't affect how we see it. Alright. Now, remember how in the last section of chapter 5 we introduced a test for convergence called the ratio test, and we said this one is going to be important because this is usually the best one to use when there's factorials involved, and we said there's going to be a lot of factorials in chapter 6. And the reason there's a lot of factorials is because our process for building power series tends to generate them. Okay, remember we differentiated over and over again when we were building the power series for y equals e to the x, and that caused us to have an increasing list of numbers we were multiplying together, a 2 and then a 2 times 3 and then a 2 times 3 times 4. Well, it turns out that that's usually what happens when we build a power series. So factorials are a very common feature. So what that means is it's usually going to be the ratio test that we use to determine their interval of convergence. Now the exception to that is if the power series happens to be a geometric series, then we can just use what we already know about the restrictions on the size of R for a geometric series to converge. But otherwise, we're going to have to use the ratio test. So remember, for the ratio test, we're taking a limit as n goes to infinity of an absolute value of the n plus 1 term, so x to the n plus 1 over n plus 1 factorial, divided by the n term, but of course to divide by a fraction we need to multiply by its reciprocal. So I'm going to multiply by the reciprocal of the n term. Okay, now before I try to compute the limit, I can do some simplifying. X to the n plus 1 over x to the n. The bases are the same, so I can subtract the powers, and that's just going to leave me with an x. So this is a limit as n goes to infinity of the absolute value of x over, now let's look at the factorials. N plus 1 factorial is n plus 1 times n minus 1. It goes all the way back to 3, 2, 1. N factorial is n times n minus 1, and it goes all the way back to 3, 2, and 1. Which means that everything cancels except that n plus 1. So now my limit is the limit of the absolute value of x over n plus 1 as n goes to infinity. Okay, now even though x is a variable when we're thinking about the function, for purposes of this limit, x is fixed. The only thing that the limit is allowing to vary is n. So if x is fixed, and we're taking a limit of a fixed number over a number that's going to infinity, we get 0. Okay, so the ratio test tells us, remember, if our limit was anything less than 1, convergence. The ratio test tells us that our series, where the nth term is x to the n over n factorial, our power series, converges. And it didn't matter what x is. It converges for all x values. Now sometimes the value of x will affect our conclusions, but not this time. And this is kind of what we expected. We expected this one to converge for all x values because it kind of looked like we could just keep increasing the degree and it would just keep spreading out further and further following the function. Now maybe we just didn't go enough to find our wall, but now we have confirmation there is no wall. The interval of convergence, remember our goal was to find the interval of convergence and the radius of convergence. The interval of convergence is negative infinity to infinity, all real numbers. Now when the interval of convergence is infinitely long, then we say the radius of convergence is infinity. the radius of convergence is infinity. All right, that takes care of number 20. Now let me see what was next on the list. Next on the list was number 13. So same instructions. We're trying to find the radius of convergence and the interval of convergence. So let me jot this one down. Number 13. So we've got a sum from n equals 1 to infinity of 2x quantity to the n over n. Well, let me see. Let's see what we can do with that. Now, the bottom is polynomial. The top is exponential. Exponential means geometric, which means there's some hope that we could use the ratio test and get somewhere with it. If the bottom and top were both polynomial, the ratio test wouldn't help us. Okay, but power series always have an exponential part to them. They always have an x to a power in them. So the ratio test should always be useful for us. Let's try it out. Let's take the limit as n goes to infinity of the absolute value of the n plus 1 term, so 2x to the n plus 1 over n plus 1, times the reciprocal of the n term. Alright, so again, I can subtract these powers, and I will just be left with 2x to the 1. And when I look at these, there's no real obvious way to simplify n over n plus 1, but I don't really need to simplify it because I know that as n goes to infinity, n over n plus 1 goes to 1, which means that my limit is just going to be the absolute value of this 2x that's left. Alright, so how do we interpret that? Well, remember, for the ratio test, okay, if the limit is less than 1, we can conclude convergence. Conclude convergence. Okay, if the limit is greater than 1, conclude divergence. Okay, if the limit is greater than 1, conclude divergence. But then there's a third case. If the limit is 1, conclude nothing. Okay, conclude nothing. Okay, this is a little difficulty with using the ratio test. Okay, if the limit turns out to be dependent on x, then we're going to wind up with a finite interval of convergence, because this will need to be less than 1 to get convergence. Okay, now we'll be able to say that when this is greater than 1, there's divergence, but we also are going to have to deal with the endpoints separately. Okay, let's think about this. If the absolute value of 2x is less than 1, then that's the same as saying that 2x is between 1 and negative 1. And so if I divide through by 2, then I can say, alright, x has got to be between 1/2 and negative 1/2. So since this interval corresponded to my limit being less than 1, I know for a fact that my power series converges in here. Okay, so let's just say that. So the power series converges in the interval from -1/2 to 1/2. So here I'm writing the notation for an open interval. Okay, now let's go a little bit further. If I say that my limit is greater than 1, well, that means that either 2x is greater than 1, or, since that's an absolute value, it could be that 2x is less than -1. This basically just means that since absolute value is distance from 0, it means that the distance of 2x from 0 is more than 1. So 2x is either to the right of 1 or to the left of -1. So that would mean either x is greater than 1/2 or x is less than -1/2. Okay. So let me see, since these conditions here corresponded to a limit value greater than 1, we can say that if this is true, definitely the power series diverges. Okay, so I'm going to need some more paper here. There we go. So the power series diverges. It diverges on the intervals 1/2 to infinity and -∞ to -1/2. Okay. Now, there was one last case. Okay. I wouldn't absolutely have to break this case down to answer the question, because I can actually answer the question now about the radius of convergence, but I actually can't fully answer the question about the interval of convergence. So yeah, let's tackle this last little bit. So this is like case 3. We looked at, alright, what if the absolute value of 2x is less than 1? What if it's greater than 1? Okay, well, if the absolute value of 2x is equal to 1, then that means that 2x is equal to 1 or 2x is equal to -1. That's the only two ways that 2x could have an absolute value of 1. It's either got to equal 1 or equal -1. So either x is 1/2 or x is -1/2. Now, here's the deal. The ratio test, I don't know why I do that. I always want to complete that suffix and make it ration. I don't know. The ratio test does not tell us what happens for these two endpoints. I'm calling them endpoints because they're right at the ends of that interval that we know does converge. The ratio test does not tell us what happens for these two endpoints. Okay, but we can examine them. I know this is getting kind of long, but this is just how it is. We can examine them individually. So let's start with when x equals 1/2. When x equals 1/2, remember our power series. Let's shoot. What was our power series? There was our power series. So our power series where n goes from 1 to infinity, and the nth term is 2x to the n over n, becomes let's think about it. If I put in x equals 1/2, then 2x would be 1, and 1 to the n is 1 no matter what n is. So that would be the series whose nth term is 1 over n. Okay, now I realize at this point this problem might be mentally exhausting you, and this may not jump out at you, but kind of block everything out of your mind except this. You know about this series. You know that it's a divergent p-series. Okay, it's the harmonic series, which is divergent. You just know that now. Okay, so x equals 1/2. It's not in the interval of convergence. Okay. So x equals 1/2 is not in the interval of convergence. Let's see if I can squeeze that in there. Haha. You know what I mean. Not in the interval of convergence. But what about the other endpoint? Well, when x equals -1/2, then our series would become so if I put -1/2 in there, 2 times -1/2 is -1. So then our series becomes the series from n equals 1 to infinity of -1 to the n over n. Now that's not the harmonic series, that's the alternating harmonic series, which is the alternating harmonic series. And the alternating harmonic series is convergent, which is convergent. Okay, so x equals -1/2 is in the interval of convergence. Okay, now I'm finally ready to answer the question. Okay, so what we're even working on, this was number 13. Number 13, answers. How do you spell answer? Answers. Okay, interval of convergence. So my interval of convergence stretches from -1/2 to 1/2. It includes the left endpoint, so we'll put a bracket to show we're including that one, but it doesn't include the right endpoint, so we'll use a parenthesis to show we're excluding that. However, this question here, the radius of convergence, we could have answered this one sooner. Radius of convergence. Radius of convergence. Okay, the radius of convergence is just the distance from the center of the interval, which was 0, to either endpoint. And it's not really impacted by whether or not we include the endpoints. Whether we include these or don't include them, or include one and not the other, that wouldn't have impacted it. The radius of convergence would have been 1/2. So remember, that's what we called big R. Okay, that we could have answered sooner before we analyzed the endpoints. All right, well that's it for number 13. Let's see what was next. All right, we got 2 more, and then we'll be done with this section. So number 23 and number 38. All right, let's have a look at number 23. All right, there's number 23. Lots of factorials. We definitely want to apply the ratio test there. So let me write that down. We've got a sum where k goes from 1 to infinity. And what do we got? We've got a k factorial squared. We've got an x to the k over a 2k quantity factorial. Okay. Yeah, I didn't really mean to do that, but little pun there. You'll find that the longer you sit and think about math, the lower the criterion for something to be funny is. I don't know why that is. Maybe just because math isn't particularly funny. Well, depends on which math, I guess. And it depends on what you mean by funny. But let's not get off on a tangent. Okay, our task is still the same here in 23. Okay, in fact, let's just read the instructions real quick. In each of the following exercises, find the radius of convergence. Okay, that's a little easier because it means we definitely won't have to be checking any endpoints. Okay, we're just looking for the radius of convergence. Alright. So, let's apply our ratio test. We're using k instead of n, so we'll take the limit as k goes to infinity. Now, we need the k plus 1 term. So I'm going to have a k plus 1 factorial squared over 2k, but that's a plus 1 in parentheses, and then the whole thing is factorialed. Okay, times an x to the k plus 1, and then a k term flipped upside down, so 2k factorial over k factorial squared x to the k. I think we did one pretty similar to this in the last section, so you might already have some idea of how this is going to turn out. Okay, let's just let's carry it through here. So limit as k goes to infinity of, alright, so k plus 1 factorial is, so k plus 1 factorial would be k plus 1 times k, and then goes all the way back to 3 to 1. But then that's squared, so I can square all of those factors. Alright, got that. Now down here, if I distribute the 2, that's really 2k plus 2 factorial. So that's 2k plus 2 times 2k plus 1 times 2k, and then all the way back to 3, 2, and 1. Now, second fraction, we've got a 2k factorial. So that's 2k all the way back to 3, 2, 1. Aha! Get a little cancellation there. Okay, slice that stuff out. And then down here I've got, well, you know, I left out my x's. X to the k plus 1. And then down here I've got a k factorial squared. So I've got a k times k minus 1 all the way back to 3, 2, 1. But they're all squared. And I've got an x to the k. Alright, but then I can cancel these against those terms. And let me see, I can also cancel x to the k with x to the k plus 1. So I've got a limit where k goes to infinity. And what have I got left here? I've got a k plus 1 squared. I better multiply that out. So that'll be k squared plus 2k plus 1. Down here, I've got 2k plus 2 times 2k plus 1. So that'll be 2k squared. Plus 2k plus 4k is 6k. And then plus 2. And actually, I made a mistake. 2k times 2k is 4k squared times an x. Now, here's the thing. this fraction, the top and the bottom have the same degree. So I can take the limit of that. The limit would be the ratio of the leading coefficients. So that'd be 1 over 4. So this whole thing goes to 1/4. X goes to x. So this becomes the absolute value of x over 4. Okay. So for convergence, we need the absolute value of x over 4 to be less than 1, which means that x over 4 is less than 1 but greater than -1. And if we multiply everything by 4, we get that x has to be between -4 and 4. So my interval of convergence is at least -4 to 4. Now here's the thing though. If I needed the full interval of convergence, I would need to go back and test the endpoints. Okay? I don't need to worry about anything past the endpoints. I'm definitely going to have divergence there. Okay? But the endpoints are always a wild card. They always have to be tested individually whenever you have a finite interval of convergence. But remember, we were only asked to find the radius of convergence this time. And now we can actually answer that question without finding the full interval of convergence, because the radius of convergence isn't really affected by the endpoints. Okay, the radius of convergence is 4. Because it's centered at 0. Okay, how do I know it's centered at 0? Because it was x to the k, not x minus 2 to the k or something like that. So it was centered at 0, and 4 is the distance from 0 to either endpoint. So that's my answer, and that's all I have to do for problem 23. Now, if it also asked me for the interval of convergence, I would need to go back and test the endpoints. Okay. Alright, there's one more I wanted to look at. Let me see here. Outline problem number 38. Okay, let's find the instructions here. They're down at the bottom of the page. So in the following exercises, alright, we're going to use what we know about geometric series to find a power series for the function with a given center and identify its interval of convergence. Well, let me see here. So 38, we're given f of x equals 1 over 2 minus x. Oh, and they want it to be centered at a equals 1. Okay. Well, I did something like this earlier, but I wanted to run through one more like it before I closed out the section, just because this is kind of a novel algebraic manipulation, and I thought it would be good to see it one more time. Alright, so let me write this down. 38, we're given f of x equals 1 over 2 minus x, and we're also told that a is 1. Alright. So this part here means that we need to center our series at 1, which means my r value down here needs to be an x minus 1. So the first thing I'm going to do is I'm going to replace x with x minus 1 plus 1. Okay, that's what it's going to allow me to get the minus 1 that I need. And then let me see, that plus 1, when I distribute the minus, becomes a minus. Well, that's actually kind of nice, because then I have 2 minus x minus 1 minus 1. And when I combine the 2 and the minus 1, that becomes a 1. And the reason that's nice is I won't have to manipulate that 2. So 1 over 1 minus x minus 1. So remember, here's the formula we're using. the formula we're using is that A over 1 minus R equals a sum where n goes from 0 to infinity, okay, of AR to the n, like that. So it would be A plus AR plus AR squared, and so on. So we're using that formula. So now, comparing my fraction to that formula, I've got the 1 that I needed. I can see that R is x minus 1. I can see my A value will be 1. Okay, so f of x would be a sum from n equals 0 to infinity of, there's my A, there's my R, 1 times x minus 1 to the n. Okay, so there we go. Now, what else did the problem ask for? It said find a power series with the function with a given center A, and identify its interval of convergence. Well, this is a little bit easier for geometric series. I don't need to use the ratio test. Okay, I can just hop right to the conclusion that my R value needs to be between -1 and 1. So x minus 1, it's got to be less than 1, greater than -1. Now if I add 1 to everything, then that tells me that 0 is less than x is less than 2. I don't need to test endpoints on an interval of convergence for a geometric series. For a geometric series, the endpoints are never part of the interval of convergence. Okay, so the interval of convergence is the interval from 0 to 2, not including the endpoints. Alright. Well, that is everything I wanted to do for section 6.1. I hope you all enjoyed that as much as I did. I realize it makes me a little bit of a math nerd to enjoy doing that kind of stuff, but I think it's kind of neat, and it's kind of satisfying to play around with that stuff and see everything come around so nicely. And I kind of suspect that since you're in Calculus 2, you might not have hung around quite this long if you weren't starting to find this stuff kind of neat too. I hope you are. I hope you enjoy this, because this is what you've chosen, and I hope you find it interesting. Alright, well, as always, if you have any questions, contact me anytime. We can set something up. Otherwise, I hope everything's going well for everybody. Take care.